Okay, I think we'll get started. So today we're going to do the first of several labs involving the analog to digital converter in the PIC12F675. So that's a feature this microcontroller has, and unlike the PIC10F200, this is which doesn't have it. This offers this capability that, of course, can be very useful in the laboratory if you're trying to read any kind of analog signal. So we're going to get introduced to a couple more registers. The ANSEL, we've talked a bit about this in the setup part, and then the ADCON 1 register, and this is where this kind of controls the starting and stopping of the process of doing the analog to digital conversion, which takes several computer cycles. And then the ADRES high and the ADRES low. This is a 10-bit analog to digital converter, so it can't fit all those bits onto one register. So there's two dedicated registers for that. The high being the most significant bits and the low being the least significant bits. In the spirit of this series, we're going to try to keep things as simple as possible and focused on the assembly code and the microcontroller itself, and not worry too much about the electronic components that might make things a little bit more clean, or also necessarily the particular application. So today we're just going to supply a voltage with a voltage divider and a variable resistor trim pot up here, but you could certainly imagine this being a temperature, a thermocouple, or a soil moisture sensor, or some kind of light sensor, and so on. And then we certainly might want to relay that back to the computer, but that again is an extra layer of complexity when we want to focus on exactly what's happening here with the analog to digital conversion. So what we're going to do is we're just going to display some of the results. Now, with the PIC12F675, we don't have 10 output pins that we can use to send to a diode LED to light up according to the voltage that's being measured. But we do have a few extra. We have 4 extra. We're going to use GP0 to bring in the analog signal, and then the outputs we're going to use is GP1, 2, 4, and 5. Remember, GP3 is special. It can only be used as an input. So essentially what we're going to do is we're going to display a 4-bit analog to digital converter. So we're going to take analog in, and then it will be displayed in an LED array, which has actually has 10 LEDs, so that would work perfectly if we had enough outputs. But we only have, so since we only have 4 outputs, we're going to just use 4 of that, and then the remainder we're not going to even use. And we have these different LED displays, and we're going to send the value of the different bits in the register, starting with the most significant bit down to the 4th most significant bit, and then we're just ignore the rest. So basically it's a 4-bit converter here. And so what we would expect to see then is, the other thing I should say is you have 2 choices. You can set your range for the analog to digital converter being the voltage of the microcontroller, which is what we're going to do. So that's just the VDD, which for us is about 5 volts, like 4.97 or something like that. And then the other thing you can do is set the range based on some reference voltage from the outside source. So maybe you want to, you're powering this with 5 volts, but you want to have your dynamic range of your experiment just be 0 to 1 volt, so you would supply a 1 volt reference voltage. We're going to just work with the 5 volt reference voltage. So what that means is when we are up near 5 volts, so we turn this trim pot down to almost acting as a wire, we'll get a 5 volt resistance off of here relative to ground, and we should see all 4 of these light up. If we go to half of that. That'll be right at the transition of these three lighting up and this one off, or this one on. So we'll see if we can turn it so this one just turns on, and we should be at about 2.5 volts. And likewise, down here, 1.5 volt would be either with these two on and this one off, transitioning to just this one on. So we'll see if we can see that happen as well. All right, so let's go to the board and then go to the code. So I'll switch here now first to just the .cam and get a look at the, I'm going to see if I can, that might show up a little better. We have, this is kind of actually fortuitous. We have a spurious on here on this pin. So now we can see the difference between the on and the off in these LEDs. So we're only going to use these first 4 LEDs. Everything is set up like we've been doing. Nothing really new. The outputs, the input is going to come from down here. Here's our trim pot and our other resistor. And so that will go into pin 0. And then each of pin 1, 2, 4, and 5 are linked to this LED array. And these resistors here are just resistors that protect those LEDs. They're just 470 ohm resistors. Okay, so that's the setup. So let's switch here to the program itself. So I'm going to move this over, make sure that I'm out of the way of the screen. Okay, so first bit, all this stuff is just like we always do before. The configuration bits, the include file, and any kind of comments that you want to make. So this is just our first analog to digital test. And again, all this code can be found on my GitHub page. Here, again, always the same, sort of identifying where, orienting the program counter, identifying where that is and where the main program starts in the program counter. And as always, I've got a main part and then a main loop. The main part is where we change the things that aren't going to change, and then the main loop is the actual operation of the device, as it's going. So let's go through this again. We've kind of talked about all this before. So this 5th bit on the status register shifts us from one bank to the other. There's 2 banks of registers, and we need to be on bank 0 to clear the GPIO. Then we're also on bank 0. We're going to clear the comparator. And I don't know for sure I think some of these you can leave either way, and the analog to digital will take precedence on that, but we're going to just clear this all to 0. So you could just write clear CMON, but I'm going to keep this CMCON, but I'm going to keep this in the same format as all of our others, so that this is very consistent throughout these different labs. Then we have to flip back to bank 1 to get to the ANSEL. So we're going to now put the ANSEL here. And let's again look at what the ANSEL does. So we'll look here. A couple of things. We're only going to use bit 0 as an analog in. So that's this guy over here. And then these 3 will be digital outputs as we want. So if you go to the pin diagram for this, you'll see analog in 1, 2, 0, 1, 2, 3. We just want 0 as the analog in because we want to utilize those other pins as digital outputs. Then these, see, that's 4 bits, 1, 2, 3, 4. Then this final bit is unused, and then these 3 bits right here give the clock time of the analog to digital conversion. And I don't know exactly what I don't want to say too much about all this. I'm not a real have a real solid understanding of that. But what we're seeing here is that we're just going to derive it from the internal oscillator, the internal clock. And so, as always, we're only using an internal clock drive here. All right, so that is the setup of the ANSEL. And then finally, we need to set up the TRIS. And again, input would be pin 1. Pin 3, that's this one here, or sorry, pin 0. Pin 3 is always an input, so that has to be a 1. And then everything else we want is outputs to go to this LED array. Then we send that to the TRIS. Then we make sure we're back on bank 0 so that we can read the GPIO pins. So if we don't do that, we won't be able to read the GPIO pins later in the program. Now we need some extra stuff for the A to D, so this is also in this preliminary bit, but we don't have this in the cases where we're using the converter or using just the digital input output. And so what we're talking about here is this ADCON 0. Oh, shoot. On the board I had ADCON 1. ADCON 0 is what it is. So I'll correct that at the end. So this is a new register for us, and what we're going to do here is, let's look at page 43 on the data sheet. And here's the ADCON 0 register. And the important bits here are the AD on bit. So we want to start that with it being off. And then this is a this is the go bit, and then it'll change automatically when it's done, but we have to start that with the go bit. So bit 0 and bit 1 are going to be important in reading in the analog to digital signal. Then up here in this one, the 7th bit, that's a 0 here. So that means that this is what chooses how we save those data to the 2 registers. Because remember, we need 2 registers. And so we have to go back to page 42 and look at that. So if it's 0, which is what we have, we're gonna put the 8 most significant bits in ADRESH res H, and then the remaining 2 bits in ADRESL, with the least significant bit being the 6th bit of ADRESL, and the most significant bit being the 7th bit of ADRESH. Had we put a 1 over here, then we would have shifted this so that the 2 most significant bits show up as bit 1 and bit 0 in the ADRESH, and then the remaining bits with the least significant bit being at the 0th bit of the ADRESL. And so we'll just set it up this way. It doesn't matter too much how you do it in most cases. I can't think of a case where it would really be all that important. But then I guess the one case about this is if you just use the ADRES when we're in this configuration, then you're essentially using, if you just ignore the ADRESL, then you're essentially just using an 8-bit converter. So that might be useful at times when you don't need a 10-bit. You don't need to worry about the other register, as is the case for this experiment. But we're even going further. We're just going to read the first 4 bits. Okay, so now we launch into the program. And so let's go ahead and look at what's going on here. We're simply going to clear all of our pins set to 0. So our output will initialize with all the LEDs off. Then this start here, this is the start. This is pretty simple code, but and it's a little confusing in the. Or I found it a little confusing in the data sheet, it feels like you need to do a little more than this, but this works. So we take the ADCON 0, turn that to 0, and the ADCON 0 and turn that to 1. Then we now are going to, so this starts the process, and that will just happen automatically. And when it's done, and it'll move on. And then what we will see here is we will read in the 4 most significant bits here. So the way we set things up, that'll be 7, 6, 5, 4, and we'll assign that to pins 5, 4, 2, 1. And then I tried this without a delay, and then we wouldn't need any of the delay code here that we've talked about in some other videos. The first video in this series, a little bit, and then a lot in the PIC12F675 series. So if you aren't familiar with the delays, go ahead and look at those videos. But we do need those. And if you want to just copy in this code from the GitHub, that's fine too. All this is doing is just putting a very small delay in, and then it goes back to the main loop. And that seems to have everything work properly. For some reason, it feels like it should work if you just put a couple of no-ops there and let it loop back, but for some reason it wasn't working for me, or I couldn't get it figured out. So I just left the loop in there. Okay, let's go ahead and build this. So this should build, hopefully. And I've talked about this in earlier videos. When I'm using a lot of the inputs, especially analog inputs, I like to power the PIC during the programming with the PIC Kit 5, and then switch in the run, when it's just running, to an external power supply and not run it with the PIC Kit 5 attached. And so, for example, here I don't have any voltage coming in yet until we turn this on. Okay, so now let's build. Or so we did build. Let's write this to the chip, and hopefully this will work. Uh-oh. Let me see. It looked like it worked. I've never seen that pop up before. So hopefully it'll still work. So let's give it a try. So I will take this off and now plug in the voltages. And so this needs to go to pin 0. And let me turn on the voltage here. And let's see if this is working here now. So I'm going to turn this up to, let me turn it all the way up. So let's get those that we had on the board there. So here I am at full voltage basically, and we see all the LEDs lit up. So I should be able to get the 3 to go off at around 2.5 volts. So let's try that. It's starting to go off. It's just digitally counting. And then at 2.5, 2.2. Okay, so now they're all off. And the first one's off and the other's on. So let's bring that up a little. Now what's happening, let's see here. What's going on? There we go. Notice when I put my screwdriver here, these come on. So it's acting as an antenna, a pretty effective antenna. So we're getting wild fluctuations there, and it's apparently reading that. So here we are at 2.6. Let's see if I can take that a little bit lower. 2.5. Should really be like 2.49. Yeah, you can see these just flickering here. So a little bit above there, and there we are at that voltage. Okay, so now let's turn it down to 1.25, and that should be our next sort of benchmark of this. And again, as my screwdriver's in there, It's acting kind of as an antenna, so we're not getting it to work to look perfect as we go here. But I think as we there we go. There's 3327. It's a little harder to get it exactly right when your screwdriver's in there. Maybe a plastic screwdriver would work better. 2.6. So yeah, it's really quite close to what it should be. Let's see if I can go even closer. Yeah, there it's a little bit less, and those are all on. No, hard to get it exactly right, but it's doing what we thought there on the board. And then let me turn this down as far as I can. That only goes down to 1 volt, and so we're now shut off those top two because we're below 1.25. All right, so this is the analog to digital converter, and we're able to just kind of recap the important things. We get the analog conversion started with this little bit of code, and then this is stored to the first 8, or all of the ADRESH, and then the first 2 bits, bit 7 and 6 of the ADRESL to get the full 10 bits. And of course, we're not looking at that, but we're seeing just the top 5 here. All right, so I think that's a good place to finish here with the analog to digital conversion, and we'll be moving on to some additional labs where we use this feature of the PIC12F675.